All right, so we're done through naming. Now we're going to just get into some common acids. Naming bases, it's just regular names like sodium hydroxide, calcium hydroxide, so there's no special naming system for bases. So we're done through with naming. Practice those. Common acids. Sulfuric acid, there's just a few listed in your book, and we're just going to kind of focus on those. Sulfuric acid, what's special about it, it is most used in the world. It is also what makes it can be somewhat dangerous just because it's used in pretty much every country, and in some cases people can get their hands on it and use for bad purposes. And I'll show you a video about it's happened a lot in different countries, but I'll show you a video about a model named Katie Piper who had acid thrown in her face by a person hired by her ex-boyfriend. And it's just horrible, but it's happening in way too often by people who are dumped or upset, and they're ruining people's lives with this stuff. It's in your car batteries that you're in your cars, along with lead. It's in your car batteries to create a voltage and get your car going. But there are other chemicals in there, but those are the two majority of what's in there is lead plates, which makes the car battery heavy. And then sulfuric acid is also in there. And so if you ever get any liquid coming out of a battery, I would be careful with it. I also dehydrate sugar. I don't have this demo ready for today. I was getting the other ones ready, but some people have said that they've seen this before, where you put sugar, just regular table sugar, which is C12H22O11, and you add concentrated sulfuric acid, and it takes the water away from the sugar. Well, if you take water or hydrogens and oxygens away from C12H22O11, you have carbon. And it creates this big tube of black stuff with air pockets in it. Anyone seen that before? Yeah. It's very stinky. It smells like really strong brown sugar, like irritating. Yeah, we'll do it in the hood, and we can show that to you next week, because some people have seen it, some haven't. Nitric acid. Nitric acid, very nasty odor. In biochemistry, we'll put it onto different foods to see if there's protein in it, because it always turns yellow. And with protein, it goes through a chemical reaction. I remember doing this a lot in college chemistry courses, working with nitric acid and ending up with brown and yellow hands afterwards. Saddam Hussein, I read an article about how he would use nitric acid, dip people in nitric acid as a form of torture to try to get them to talk. Also used in making explosives, rubber, dyes, etc. All of these are very much used in industry, in making things. Hydrochloric acid, if you go to Hardware Hank, you can go buy muriatic acid. It is hydrochloric, just another name for it. You use it to adjust pH. If you have a small pool, you can just go to Walmart or wherever and buy a pH down, pH up type granules. But if you have a huge pool, adjusting the pH would take forever with those things, or a bigger pool. So you use actual strong acid to do that. I need to get some this summer and clean our driveway off, which has iron stains on it, and it's a good way to clean iron stains off of masonry or concrete. More on that. This is also what's in your stomach, hydrochloric acid. We'll talk about that more in a bit. To use a pickle iron and steel, which is just cleaning off any impurities off the surface, because it will react with any iron oxides that are on the surface of iron and steel. So cleans it up. Acetic is another common acid. Most of you probably have this at your house. It is vinegar. Or vinegar is acetic acid. It's a weak solution of acetic acid, about 5% solution. And it already tastes kind of crazy. Just imagine if it was 50% or something. It would not be good for you either. But it is a weak acid, but it is strong, strong taste. Last one we'll have on here is phosphoric acid. I will drink some phosphoric acid tonight, as I love my Cherry Pepsi. And Cherry Pepsi and all colas have phosphoric acid in them. What type of acid is in like Mellow Yellow Mountain Dews? Citric acid or squirt. But There's your citric acid, which is naturally found in oranges, lemons, which then gives you that citrusy taste. It's also used, most used for fertilizer and animal feeds because you gotta get that phosphorus into fertilizer. You need phosphorus and nitrogen, and that's one way of getting it in there, just putting in phosphoric acid. It's just a weak acid, whereas nitric acid is a strong acid. So this is a weak acid. It's in your sodas. It helps bring the pH down to 2 and 3 in your sodas, but it's not like drinking a strong acid, which would be harmful. So watch a video about Katie Piper after this. Properties, let's get into bases. Properties we discussed yesterday. They do taste bitter. Remember the unsweetened chocolate from 9th grade if you did that. It also changes the color of indicators, like we talked about yesterday. Phenolphthalein. Phenol, now what spells? pH, silent pH. Phthalene. Turns what color in presence of a base? Pink. Yep. And litmus, these are two that I would want you to know. How about litmus? In a base? Blue. Blue. So both acids and bases can turn indicators colors because what you're doing is you're adding or removing hydrogens, which changes their chemical structure. They feel slippery like soap. We talked about that yesterday. If acids react with bases to produce salts and water, then bases react with acids to produce salts and water in neutralization reactions. And like we talked about yesterday, they conduct electric current. Acids and bases do, and so do neutral solutions that have electrolytes. They all do. A strong base will conduct more than a weak base. A strong acid will conduct more than a weak acid. You might say, well, what about a strong versus a weak, or strong base versus a weak? Yeah, strong base versus a strong acid. Just depends on what the molarity is at that point. The one that has a higher molarity will conduct more because there's more ions. All right. Now we're going to get into different definitions of acids and bases. There are 3 different definitions of acids and bases, which is a little bit frustrating and annoying, but all 3 of them are slightly different, and all of them have been always put into different chemistry books because they all can explain different chemicals a little bit differently. I'll show you what I mean by that. So I have Arrhenius acid. Arrhenius is a scientist, and he decided, he's the first person that described what an acid was, and he said that it increases the number of H+ ions, or hydrogen ions, in an aqueous solution. None of the other definitions say it has to be in water, but Arrhenius does. It says we're going to increase the H+. Well, how do you do that? If you put something in water that has hydrogen and it breaks apart, we're going to make more H+. For instance, hydrochloric acid. Put it into water, it will break apart. The hydrogen will attach, to the water, transfers to the water, and you make this hydronium. This is a hydronium ion here, H3O+. H3O+ hydronium is very important because the more of that, and that's what makes an acid, is that ion. The more of that ion that is made, the stronger the acid. The more of that ion that is made, the lower the pH. We'll talk about how pH is calculated on Monday. But it's all about that ion right there. So if you make more of that, you've got yourself a stronger acid. Now, the next one is weak. What do you notice different about those 2 equations? One's HF, one's HCl. What else? One's got a double arrow. Yeah. What that means is this goes to the right and to the left. It's in equilibrium in both directions. When it says strong and I got a full arrow here, that means that 100% of HCl's break apart. 100%. So if I have a solution of HCl, I actually would not expect any HCl's stuck together. None. I would expect water molecules. Some of the water molecules I'd expect to have a hydrogen on them, and some hydroniums would be there, and I expect to see just as many Cl's there as hydroniums. but I would not expect to see any HCl's. Whereas with this weak acid, which does not break apart very much, I would expect to see a lot of them, some of these, but less, some of these, and some water that has not had a hydrogen attached to it. But I would expect to see all those things if I had that ultimate superpower and could see all the ions and molecules in a solution. I would expect to see all of those things in there. Why in the world do you think it might be that this is a strong acid and loses its hydrogen pretty easily, and HF does not lose its hydrogen very easily? Anything from the past that you might remember that might cause this to be a stronger bond? Electronegativity. Yep. Fluorine has such a high electronegativity, it causes this bond to be stronger than the HCl. So a stronger bond causes it to lose its hydrogens less, causes it to be weaker as a acid because it doesn't lose hydrogens as much. Kind of crazy. All right. Bronsted-Lowry, what's their definition of an acid? Their definition is that it's a molecular ion that is a proton donor. Proton donor. That's an H+, a proton. How many protons are in a typical hydrogen atom? Hydrogen atom. How many protons, Eric? 1 proton. All right. How many electrons in a hydrogen atom, Rachel? 1. No neutrons in a typical hydrogen atom. So now if I make it an H+, there's no electron. What you have left is a proton. So when it says proton, it means H+. When it says H+, it means proton. They're the same thing. All right, so Bronsted-Lowry, how I've always remembered it, BLTs, I like BLTs. Well, this is BLP. Bronsted-Lowry goes with proton. The definition is always about protons. In this case, an acid is a proton donor, or it gives it away. Notice up here, both of these acids, it works for these also. Both these acids give up their hydrogen to water. They give them away. They're donating in hydrogen to somebody. All right, does not need to donate in water, according to Bronsted-Lowry. So there's one area where it's a little bit more of a broad definition. Does not need to be in water. Up here it says has to be in aqueous solutions. Bronsted-Lowry say, well, it could be in a gas. The same thing could be happening in a gas. It's possible. All right. What about bases? Their definitions are a little more different. Acid definitions seem pretty similar. Arrhenius bases and Bronsted-Lowry bases definitions are a little different. So let's talk about that. First of all, it's any chemical which increases the concentration of hydroxide ions. Hydroxide ions. Hydroxide ions are what? What's the formula for that? OH minus. Okay? So hopefully it makes sense to you that if I take NaOH as a solid and I throw it into a beaker of water, what types of ions am I going to get? That ionic substance breaks apart into NAs and OHs. So pretty easily, I can increase the number of OHs by just taking a solid hydroxide and dissolving in water. So that's definitely a base. It's increasing the number of hydroxides in solution. So our strong bases are all hydroxides. Sodium hydroxide, potassium hydroxide, barium hydroxide. They're group 1 and 2 hydroxides. Strontium hydroxide. Our group 1 and 2 hydroxides are our strong hydroxides because you put them in the water, they dissociate. Some of them dissolve better than others, but when they break apart, you get a bunch of OH, which makes it basic. All right, what about ammonia? What's the formula for ammonia? NH3. I heard both, but it's NH3. Ammonium ion is NH4. So if I put ammonia into water and it acts like a base, what it's going to do, it's a weak base, so I'm going to do double arrows. What it's going to do is pull a hydrogen from the water. Acids would give a hydrogen to water. NH3 is going to pull hydrogen from water. So what's that going to become as it gains a hydrogen? NH4 positive, because it gained an H plus. What's left of the water there, Steph? If I take the hydrogen away from water, what's left? Oxygen. And if I take one hydrogen away? Yep, I have hydroxide. So did I increase the number of hydroxides? Did I still do that? Yes, I still increased the number of hydroxides. It's just that it wasn't like sodium hydroxide where I just put it in water and it dissociates and makes it. It pulls the hydrogen from water. And if anything is a base that's not a hydroxide, this is how it has to work. It has to pull hydrogen from water to create OHs. So there's a lot of bases out there that are not hydroxide, and this is how it would make it happen. So just like acids have more H2O pluses, the more OH minuses, the stronger the base. The stronger the acid, the more H2O plus. Moving on. What about Bronsted-Lowry? Well, Bronsted-Lowry is all about the proton. It's not a, here's our BLP again. Bronsted-Lowry proton. Just need to remember which one's which. Acids are donators, bases are acceptors. It could be a molecule or an ion. We'll see that in a little bit, what do we mean by that. So like we just saw, ammonia accepts the hydrogen from water. That's how it's a Bronsted-Lowry base. And you might say, well, how is a hydroxide a Bronsted-Lowry base? It also, those OHs can then take hydrogens from water and then create more OHs in turn. So any type of base is also going to pull hydrogens from water. So Arrhenius base says you have to increase OH minuses in solution. Bronsted-Lowry says, well, as long as you pull a hydrogen, if it's a hydrogen plus acceptor, that makes it a base. So different definitions, but both things that we know as bases typically fall into those definitions. Do know the different definitions. That's one of the fun parts here. All right. Getting into the Bronsted-Lowry part of it, we're going to start naming acids, conjugate bases, all that jazz. Mono means one. Protic, what do you think? In this case, what do you think it means? Proton, or H plus. So 1, H plus. So it has one hydrogen to give. So HCl, one hydrogen give. HI, one hydrogen give. HNO3. Acetic acid would fall into this, because even though it has 4 hydrogens, it only loses the one. The other 3 stay with the ion. So it has one hydrogen give. Pretty much for our purposes, it has a hydrogen in front. One hydrogen in front. That means that it is monoprotic. Oh, let's not do that yet. So here's just an example of that happening. With the HCl breaking apart, giving up its one hydrogen, and then it's done. Diprotic, that means it has 2 hydrogens it can release. This is sulfuric acid. 2 hydrogens in front. This is a minus charge up here. It can be tough to see that different color. And a minus charge here. So, which one do you think is strong? Which one do you think is weak? Which one do you think is strong? The top equation or the bottom? What's that? Top is strong. Why, Cody? Yep. And how do you know 100% goes to the right side? Because of the one arrow again. Yep. So this one arrow tells me that 100% of this first hydrogen is released. So when I say that H2SO4 is a strong acid, that doesn't mean it loses both hydrogens right away. It means it loses the first hydrogen right away. It doesn't just lose them both right away. If I had a solution of H2SO4, I would not expect to see any H2SO4s in it. I would expect to see water molecules that don't have a hydrogen attached. I expect to see hydroniums. I'd expect to see these bisulfate ions, they're called, HSO4s. I expect to see them again, more waters, more H2O plus formed, and then some sulfate ions. But I would not expect to see any H2SO4s at all. Now these guys, this is highlighted a different color. Let's talk about why. as we label these, we have our acids on the left. Why are they acids? What are they doing for hydrogens? Are they gaining them or losing them? As we go to the right, what's H2SO4 doing? Losing. That's what acids do. H2SO4 is losing the hydrogen, becoming HSO4 minus, which is its conjugate base. Those guys are an acid conjugate base pair. Water, in this case, is gaining a hydrogen to become H3O plus. So that makes it a base, and this is its conjugate acid. What's special about HSO4 minus in this case is that here it's a base, and here it's an acid. That makes it have a special term to it, which is called amphoteric. Something that is acting as an acid and a base in the same solution. It's acting as both. Just like ambidextrous means you're able to use both arms or hands well. Amphoteric means it can be both acid and base in the same solution. Moving on. Triprotic. There is no quadprotic or pentaprotic. This is it. 3 is the most. So it gains 3 acidic hydrogens. Good example is phosphoric acid, which is going to be in my cherry Pepsi I'm drinking tonight for supper, which I'm looking forward to. If I had to pick, cans would be better. But I currently have bottles at home because they're cheap penny pinchers. But I do like cans better.
Are you more of a 2 liter? They'll stay cool longer.
No.
There's milk here.
I love milk. Love milk, but milk doesn't love me. All right. We're bringing it back. We're bringing it back. Sorry to those of you listening on Schoology. Here we have phosphoric acid. Strong or weak? Weak. All the way through, right? Weak, because it's double arrow. So when I'm drinking my cherry Pepsi tonight, I have a weak acid that I'm drinking. Which of these ions would I expect not to see in my cherry Pepsi? Or would I expect to see all of them? If I had the ultimate superpower and I could float through my cherry Pepsi and see ions and molecules, what would I not or what would I expect to see? Tron? The phosphoric acid is in my cherry Pepsi, and it's a weak acid. And I know that because it's double arrow. If it's a full arrow, that would mean that this hydrogen is, the first hydrogen is given up completely. What do you think, Casey? It doesn't have this? H3PO4 is what is dumped into it originally. What's that? Like this one right here? Just see that one? Okay. Sorry. Anyone else? Good guess, though. Anyone else? I am going, phosphoric acid would be a solid. It's just dumped into it, dissolves when they first make it. Here's what I'm going to see. I would see them all. Because some of these are going to break apart, but not all of them. And we're going to make some H2PO4. Now, some of the H2PO4 are going to give up hydrogens, but not all of them. And I'd see some HPO4 2 minus. Some of them will break apart, but not all of them. And I'll see some PO4 3 minus. I would expect to see the least of these guys, however. Because a weak acid means like about 1 in 100 would be the most that would break apart. So I'm not going to break much of this apart. And then when I do, I'm not going to break much of this apart, even less. And when I do, I'm not going to break this apart, even less than the last one. So I just keep seeing less and less. But I'd expect to see all those in some amount. Everything would be in there. Only with a strong acid, that strong one at the first would not be seen. All right, let's label these things. What is everything in this first column here? Acid or base? acid. They are all losing a hydrogen left to right. Water is then our base. What is the H3O plus acting as? A conjugate acid or a conjugate base? Conjugate acid, yes, because it is what the water becomes when it loses or when it gains a hydrogen. And over here we have its conjugate base. It is what the acid becomes when it loses one. Notice why this is, hopefully, that like H3O is an acid because as you go to the left, what does H3O do? Loses a hydrogen, so acts like an acid. What's H2PO4 do if it moves to the left? It gains one and acts like a base. So in this case, we have two of them that have different colors because they are both. There's two ions in this case that are acting as amphoteric substances. Both of those are amphoteric in my Cherry Pepsi. Those ions are there. All of them are there. Some of them are grabbing onto hydrogens. Some of them are losing hydrogens. And they're happening at the same time. They're floating all over the place. And they find a hydrogen, grab it if they can, give up a hydrogen if they can. Just depends on what else is around them, really. All right? Something you need to jot down on your sheet that is not on your sheet. And really all I need you to have is a definition. That's all I want you to understand about Lewis. Lewis is a third definition for acids and bases. And I know you don't have it on your slide. Just jot it down. A Lewis acid, and even just this is, it accepts an electron pair. It is something that accepts an electron pair. It's a Lewis acid. When I put deodorant and antiperspirant on this morning, I put on an aluminum compound. And the aluminum ions in that antiperspirant is a Lewis acid. How does that work? Let me just show you. You don't need to be able to draw this or anything. I just want to show you real quick. What happens is it joins up with water. And it accepts an electron pair. Water has two electron pairs. One of them bonds to the aluminum, and it creates, actually 6 of them would bond in the end, but we're not going to go there right now. It would create a covalent bond with the waters. There's actually would be 5 more around here, but we don't need to talk about that. And it would make these covalent bonds with a bunch of waters. In the end, it ends up releasing a hydrogen, and that's how it becomes acidic. But it's quite acidic, and it can stain your clothes and your pits because of it. It's quite acidic. So a Lewis acid in this case is the aluminum because it accepts an electron pair. The water in this case is a Lewis base because it donates an electron pair. So this would be a Lewis acid. This would be a Lewis base. And really all I want you to know about Lewis base is that's its definition. It donates an electron pair. You're not going to have to identify them. But a Lewis base donates an electron pair. A Lewis acid accepts an electron pair. They're the opposite of Bronsted-Lowry. Bronsted-Lowry acid is a proton donor. A Lewis acid is an electron pair acceptor. That's how I always remember those two differently. Last slide. Neutralization reactions. Well, we've already discussed them a little bit. I just want to go over another one with you. This is hydronium and hydroxide. They end up making water molecules. They also form a salt. In your tummy, you have hydrochloric acid. You have a strong acid that is formed. All of us have a certain amount of acid that we form every day. Does anyone know someone who has acid reflux? Okay? Acid reflux is a nasty thing where extra acid is formed and it comes up the esophagus. And if you've ever had heartburn, you will someday probably, all experience at some point, but heartburn really hurts, and that is acid coming up your esophagus. Now if you have acid reflux, that's happening pretty much every day. So they produce too much acid. So what can they do? My sister-in-law takes a purple pill every day, Prilosec, and that purple pill reduces the amount of acid that she makes naturally. So some people produce more acid naturally than others, just like some people produce more cholesterol naturally than others. It's an hereditary trait. So she produces more acid than normal. She takes this purple pill. It reduces the amount of acid formed. That would be a proactive approach to acid in your tummy. What about me, who gets heartburn just every once in a while? What would be my reactive approach? Tums, Rolaids, Milk of Magnesia, Mylanta, something at Walgreens that I go by that says antacid. All right? It is something that's a base that is going to try to fight that acid. So here's an example. Here's an example of a reaction. If you go to Walgreens to buy Milk of Magnesia, you are buying a suspension, essentially, because it doesn't dissolve very well, and it's going to say to be sure to shake well, of magnesium hydroxide. It's a little chalky tasting. Chalky. So in your stomach you have HCl. It's about 0.1 molar. It's not that strong, but we have HCl in our stomach that helps digest and process. Those two, if you have too much, we can reduce it with an antacid, with an antacid. What are my products going to be? Anyone? MgCl2. Those are both the ions, and they'll just be no acid or base. That'll be great. They'll just go through with the rest of the food. What else? Wawa. So we have water and some neutral ions here formed, and we've neutralized that acid. So if you're taking an antacid, that is just going to be a weak base of some sort. This one a fairly strong base. But you have a base that's going to try to neutralize part of that acid. What else is in your stomach that helps digest your food? What's that? Muscles? Yep, that cause peristalsis. Yep, that cause this back and forth motion of mixing everything that's in your stomach. Enzymes are in there. Enzymes are there to start breaking chemical bonds. They chop proteins into amino acids. They chop up the fats. They chop up the carbohydrates and starts breaking everything down. What else is in there? Bile gets in there, not in the stomach, but in the small intestine. It's formed in the liver. If you have a gallbladder, which most of you do, I happen to not have a gallbladder anymore, but if you do have a gallbladder, there's bile stored in your gallbladder. And what happens is there's messages sent. I mean, all this stuff is quite amazing, I think, but there's messages sent where you have fatty foods that goes to your stomach, gets to your small intestine, and the small intestine goes, fatty foods, we need bile. And the gallbladder goes and squeezes some bile into the small intestine. Now, I had gallstones. I had pains underneath my ribs really bad, and I went in and had an ultrasound done, and they said, you have gallstones. We're going to remove your gallbladder. So now, if I eat fatty foods, the message is still sent, but it comes directly from the liver. And not quite as much comes at one time. So fatty foods for me is not always very great on my system because I don't have all this bile just stored up ready to be squirted in. It's like quickly, get some sent from the liver, and it doesn't happen quite as quickly as those of you that have a gallbladder. It just goes there right away. So